Hi guys, welcome to Gatematic. In the previous lecture, we saw the transient in transmission line. What will happen to the transmission line if sudden short circuit fault or three-phase fault occurs? Okay, so we saw that concept. Also, we derived some expression of maximum momentary current and symmetrical current as well as asymmetrical current. Okay, now in this lecture, we will see the same concept in alternator, that is the transient behavior in alternator, that is in synchronous machine. So let's get started. Before proceeding further, I am assuming that you know the basic of synchronous machine, means how the EMF is induced in the synchronous machine. As we know that synchronous machine is the doubly excited machine, means we give field current on the rotor, that is the DC field current, which produce the field flux, and that rotor will rotate in a space which cuts the three-phase winding in the stator, and in a stator we get the three-phase voltage, that is three-phase EMF induced on the stator. That is the basic concept of producing three-phase EMF in synchronous machine, right? So if I will talk about the equivalent circuit, then equivalent circuit of synchronous machine will look like having EMF E. I am drawing the per phase equivalent circuit. It is having EMF E, that is denoted as EF, and it is having some internal reactance as well as resistance drop. Now generally in synchronous machine, X by R ratio is very high. Okay, that means we can neglect the resistance for the analysis of fault. Okay, you can consider resistance also, no problem, but to get the maximum fault current we can ignore this resistance because the value of resistance is very low. So overall equivalent circuit of synchronous machine at no load will be EMF, that is the per phase EMF in series with synchronous reactance. Okay, now if you have gone through the synchronous machine part, basic of synchronous machine part, then you know that how to draw the phasor diagram at no load. Whenever the rotor rotates, first we will give the flux. Flux is induced on the rotor by supplying the DC current IF, that is known as field current, which is responsible for producing flux phi F. Okay, now this flux cuts the stator winding, and stator winding are oriented in 120-degree space displaced. Okay, that means EMF is induced in phase A, phase B, phase C, that will be 120-degree displaced from each other. In this way we get the three-phase EMF. So the EMF induced on the stator will lag behind the flux by 90-degree, that we know. So phasor diagram of EF will be something like this, and this phasor diagram I draw at no load. At no load, what will the current produce here? So current will be 0, means electrical power transmitted by this machine will be equal to 0, and we know electrical power is equal to P max sine delta, or you can say EV upon X sine delta, means initially delta will be equal to 0 at no load. That's why I represent the equivalent circuit as EF at an angle of 0, because here delta will be 0 at no load. Now suddenly what I am doing, I want to see the transient behavior in alternator, that is the synchronous machine. So anyhow we need to change something. Okay, so suppose at the terminal of this synchronous machine I am short circuiting this, means a sudden fault occurs, that is the symmetrical fault occurs by short circuiting this, and this is the per phase circuit. So definitely the current, let us say fault current, will be produced because of this, and this fault current I can easily write, that is equal to EMF induced in the alternator divided by J into X, right? So if I will talk in angle, then it will be magnitude of E by X at an angle of minus 90. I can write like this because J term will go above and it will be in minus 90, means current lag the EMF by 90-degree. That is what the fault current I will get if I will short circuit suddenly the terminal of synchronous machine. Okay, now let us try to understand the phasor diagram at load. So if you will see the phasor diagram of synchronous machine at loaded condition having load impedance that is equal to 0, then definitely this is my phi F, same as the previous case at no load, and here EMF will be induced, this will be my EMF. Now fault current will lag EMF by 90-degree, that we saw after deriving this I fault is equal to E upon Jx. So where will be the fault current? The fault current will be somehow here, let us say this is armature current. fault current I am writing, that is equal to armature current. So because of this armature current, the flux will produced in the armature and that will be in same phase with the armature current. So phi AR will be produced in the same phase with the armature current. Okay, now see what is happening. This flux produced because of armature current is opposing the field flux. So overall demagnetizing effect we saw because of this fault, right? So what is the disadvantage of demagnetizing effect? It tries to demagnetize the overall field flux, means it tries to decrease the field flux. But according to the magnetic inertia, we know according to magnetic inertia, the flux will not change instantaneously. Okay, this is the property of magnetic material, that it won't change all the dipoles instantaneously. It will change the slowly, but it won't change instantaneously. Because of this property, some extra flux is created, some extra flux is generated in the armature that will try to overcome this demagnetizing effect. So to overcome this demagnetization or to maintain field flux constant, there will be opposite flux is generated in damper winding and field winding, which tries to overcome this demagnetizing effect, means which tries to maintain this field flux constant. Okay, so because of this armature reaction, because of this armature flux which is demagnetizing in nature, some extra flux will produce which will oppose this armature flux in order to make the field flux that is constant. Got it? So that extra amount of flux which will be opposite to this armature flux is known as damper winding flux and field winding flux. Again I am repeating the whole scenario. When sudden fault occurs, then overall current becomes very high, right? Which produces the armature flux which is demagnetizing in nature, means this armature flux tries to decrease the field flux because of demagnetizing effect, right? But due to inertia, flux can't change instantaneously. Okay, so to overcome demagnetization or to maintain the field flux constant, there will be opposite flux is generated in damper winding and field winding. Okay, that flux will try to overcome this demagnetizing effect. Whatever the concept I am giving you, that will be in transient state only. So we are analyzing these all things in transient state. So overall the equivalent circuit in that state, when sudden fault will occur, then equivalent circuit will not look like something like this. Initially the equivalent circuit I made something like this. This is my XD. Okay, this was my equivalent circuit, but due to sudden fault there will be demagnetization, and to overcome this demagnetization, some extra flux is created by this winding. This is my field winding which will produce the field flux, and this is my damper winding which will produce the flux, and these two produces the flux which will be opposite to the flux induced by this armature. Okay, this is the inductance, or you can say reactance, produced by armature. This is the reactance produced by the field winding, and this is the reactance produced by the damper winding. These all things we will get when sudden fault will occur, and this is my leakage reactance. So in initial period, what is happening? In initial period we will get four kind of reactance. First is the leakage reactance that we know. Second is the reactance produced by the armature. When current will flow into the armature, then flux will produce in the armature, and that flux will produce some armature inductance, right? And that inductance is responsible for the armature reactance. So this is my armature reactance. Now this XF, this is the field reactance and damper winding reactance, having flux which will be opposite to this armature flux. Why? Because this armature flux is trying to decrease the field flux. Okay, so some extra flux will produced that will try to maintain this field flux constant, that is known as flux produced by the damper winding and flux produced by the field winding. And remember guys, these two flux are the AC in nature, because this phi AR is AC in nature, and this damper winding flux and field flux produced in field winding, that is denoted as phi F dash, is alternating in nature, but this phi F is constant DC and it will remain constant. Fine. So because of this effect, Because of this demagnetizing effect, some extra flux will induced in damper winding as well as field winding that will be AC in nature and whose phasor will be exactly opposite to the armature phasor. Why? Because it will try to compensate whatever the demagnetization occurs in the machine. So the equivalent circuit at the initial period, that is also known as sub-transient period in synchronous machine, I will get the leakage reactance, armature reactance as well as field reactance and damper winding reactance. So overall sub-transient reactance in synchronous machine XD double dash, it is denoted as XD double dash, will be equal to XL plus parallel combination of this, that is equal to 1 upon XAR plus 1 upon XF plus 1 upon XDW. Let us denote the damper winding reactance, that is XDW. This will be my sub-transient reactance. And why this is occurring? Because of sudden increase in armature current due to fault and the demagnetizing effect. Now generally what is happening, after 2 to 3 cycle, we know damper winding is done in order to damp out the oscillation quickly in the form of losses. Means in this damper winding the losses will be more within 1 to 2 cycle initially. So losses will be more, that means the damper winding will have higher resistance and inductance will be low. So overall I can say that the time constant of damper winding will be equal to L upon R. If resistance will be high, means definitely the time constant will be less. So what do you mean by this? This means whatever the current produced in the damper winding is having the less time constant. If resistance will be more, then time constant will be less. So if any winding is having less time constant and suddenly current is produced into that winding, then that winding will go into the steady state quickly. So within 1 to 2 cycle, the current in the damper winding will go into the steady state, and we know damper winding damped out each oscillation and therefore the current in damper winding after 2 cycle will become 0. So when current in the damper winding will become 0, that means this damper winding will be open circuit. It will behave like an open circuit, and this period is known as transient period. After 2 cycle, the period is known as transient period. So initially in some sub transient period I will get the XD double dash, that is equal to XL plus this much. Now in transient period there will be no any effect on damper winding reactance. Why? Because damper winding damped out the oscillation within 1 to 2 cycle, and after that the current will become 0 in damper winding, therefore it can be replaced in by open circuited. Okay, so after 2 cycle I will get the transient period, and in transient period we will not get the damper winding reactance. So overall reactance of the machine is denoted as XD dash, that can be written as XL plus 1 upon XAR plus 1 upon XF. Okay, and this will transient period will continue till 2 to 5 cycle. After 5 cycle what will happen, just try to understand. This AC flux produced in the field winding, that is trying to oppose this the effect of demagnetization, right? So this field winding is also having some time constant, and time constant of field winding let us denote as tau f, that is L upon R. Now this is having a winding, means definitely the L of this winding is more than the resistance. So this will die out, the overall the effect of this field winding will be die out after 5 cycle. Okay, so if I will compare between the damper winding and the field winding, then I can easily say time constant of damper winding is less than the time constant of field winding. Got it? So after 5 cycle, whatever the effect produced in the armature will become 0, and the circuit will go into the steady state in which I will get only the leakage reactance as well as the reactance due to this armature. Got it? So after transient period there will be the steady state period. So during a steady state period, the effect of this AC flux produced in the field winding will also die out, you can say, and it will also behave like an open circuit, and overall the equivalent circuit I will get in a steady state period, that is the combination of XL and XAR only. Okay, that is denoted as XD. So finally I can say after 2 to 5 cycle, steady state reactance XD can be written as leakage reactance plus XAR. So what is the conclusion? The conclusion is whenever the sudden fault occur in the synchronous machine, or you can say alternator, then the reactance produced inside the synchronous machine will be time dependent. What do you mean by this? This means when fault occurs in the system, then in between 1 to 2 cycle, the reactance produced by the synchronous machine will be xd double dash, okay, which is less than the xd dash and which is less than the xd. Means overall I can say as the time passes, then overall the reactance of the synchronous machine will increase, okay, and it will move to the steady state. Obviously you can find just by drawing the equivalent circuit in sub transient period, you will get the 3 parallel lines, and overall equivalent reactance will be less than the transient reactance and it will be less than the steady state reactance. So the conclusion is that reactance produced in the synchronous machine during fault is time dependent and it will try to increase as the time passes. So there will be effect on current also. Means during initial when fault occurs in the synchronous machine at the bus bar, then at that time the reactance is very less. See, xd double dash is very less. In that case, the fault current, we already know I fault is equal to the EMF upon xd, and during sub transient period it will be xd double dash. So fault current will be very high during initial state. After 2 cycle it will be slightly low, and during a steady state it will come into the steady state. So overall I can say that if you want to find the response in the synchronous machine, or if you want to find the current equation in the synchronous machine, then it will be the combination of transient current as well as steady state current. So transient current that we already saw in the transmission line, that is the previous lecture, that is something like exponentially decreasing, okay, and overall steady state current that I got in RL circuit, that is something like this, okay. So if I will add these two, then I got the waveform something like that we saw in the previous lecture, that is something like this, okay. Now in this case I am damping out this, means I am ignoring this DC offset. I will tell you why I am ignoring this DC offset. Then overall the current will be sinusoidal only, but initially it will be more and then it will come into the steady state like this. So current response in the synchronous machine will be somehow something like this by ignoring DC offset. Means whatever the current equation we are getting in transient, that is exponential in nature, I am ignoring that and I am making the current equation. Then current equation will be sinusoidal only, but initially the peak current will be more, okay. So this is my sub transient period. I told you that for 1 to 2 cycle I will get the sub transient period in which xd double dash is very less, okay. In transient period xd dash which is greater than the xd double dash, and in a steady state period I will get the xd which is greater than the both. So definitely if I will talk about the fault current, then EF upon xd double dash, this is my sub transient fault current, or you can say sub transient current flow in the synchronous machine, that will be higher than the fault current induced during transient period, and that will be higher than the fault current induced in the steady state, because overall the reactance will increase as the time passes, means fault current will decrease as the time passes. So how the waveform of reactance with respect to time will look like? See, initially the reactance is very small, so let us consider that it is something like this for 2 cycle. This will be my 2 cycle. After that it will all increase, the reactance will increase something like this. This will be my, let us say, 5 cycle, and after 5 cycle the reactance will also increase and it will go into the steady state something like this. This is my steady state reactance xd, this is my transient reactance xd dash, and this is my sub transient reactance xd double dash. So if I will have to make the approximate waveform, then I can easily make during 2 cycle, in between 2 cycle it will be something like xd double dash. After that 2 cycle to 5 cycle it will be xd dash, and after 5 cycle it will be xd. I made the waveform of reactance with respect to time in discrete form. I can easily approximate this. This is the approximate and this is my exact value of xd, that is depending upon the time. Got it? So this much concept you need to know in synchronous machine before starting the fault. That's why I explain you the concept in this lecture. The concept is only this one. at no load how the phasor diagram is looking like, and at load sudden I short circuit this, then the fault current will induced. That fault current will be producing the armature flux, and that armature flux will try to decrease the field flux. Okay, so in order to compensate that, there will be flux produced in the damper winding as well as field winding, that will be AC in nature, and that will compensate the flux produced by this armature to maintain the constant field flux. Got it? So because of this effect, initially during sub transient period I will get the three reactants in parallel: the reactants produced by the field flux AC reactants, the reactants produced by the damper winding, and the reactants produced by the armature winding. Okay, and there will be leakage flux. During transient period, damper winding reactants will die out. Why? Because we know damper winding, the purpose of damper winding is to damp out the oscillation in the form of losses. So when losses will increase, definitely the resistance will increase, and we know that the winding is having some damper winding is having more resistance than the inductance. So overall time constant of damper winding is less. So if time constant of damper winding is like that, means it will go to the steady state quickly. Okay, so after 2 cycle there will be no any effect of damper winding, so it can be open circuited. In the same way, after 5 cycle there will be no effect in field winding, that is the AC reactance produced in the field winding, there will be no effect in that. That means that is also open circuited, and during steady state I will get only the leakage reactance as well as armature reactance. So this much concept you need to know. Now based on what we have studied, let us derive some formula that is important for you. Okay, so this much concept you need to understand. Now the last point I want to discuss, that what is the problem arises if I will short circuit suddenly the synchronous machine, the terminal of the synchronous machine. What will the problem arises? So let us say this is my EMF, and whatever the circuit I am making, that is in per phase. Okay, so if I will suddenly short circuit the terminal of synchronous machine, means this terminal voltage will become 0, and if terminal voltage will become 0, then electrical power will be 0, as we know that electrical power is EV upon X into sine delta. Now according to the swing equation that we will see in the stability, m d square delta upon dt square is equal to Pm minus P. Don't worry, from where this equation I am getting, that I will let you know when I will teach you the stability. Just try to understand, this d square delta upon dt square is nothing but acceleration, that is also denoted as alpha. So alpha will be equal to the Pm minus Pe. Now see, when electrical power I am making suddenly, that is equal to 0, and there will be some mechanical power, means it is having some mechanical power, because of that it is rotating. So because of this I am getting the mechanical power. So overall I can say the alpha is greater than 0, because here you can say m into alpha, where m is the inertia constant that I will let you in power system is stability. Don't worry, it is equal to the Pm, means acceleration is greater than 0. So whenever the acceleration will be greater than 0, means the rotor will accelerate. So this is the effect of having short circuit fault current at the terminal of the machine. The rotor will accelerate, means it will go beyond the synchronous speed, means n will be equal to n will be greater than the ns, and we know in synchronous machine n is equal to 120 f upon p. This is my ns. Okay, so if speed will increase, means overall the frequency of the system will increase. So this is something like problematic situation for power system engineer. Whenever the frequency, generally the frequency is 50 hertz. Okay, so whenever the frequency will deviate from its original value, that is the plus minus 5%, if it will be greater than the 5%, then it is a problematic situation for the power system engineer. Maybe the grid will shut down. Okay, so in order to protect these all things, in order to overcome this problem, generally we insert a circuit breaker, we insert a protective relays which removes the synchronous machine from the system. So these all things we will study in power system stability. I want to discuss here because effect of short circuit fault you should know. Okay, so this much amount of concept you should know before starting fault. In the next lecture we will start introduction to fault. Okay, so before starting fault you should know the transient behavior of alternator as well as transient behavior in transmission line. Okay, after that we will start the fault, introduction to fault, from the next lecture. So if you guys understood the concept, then please like this video, and if you are having any doubt, then you can ask in the comment below or join our Facebook group for doubt solving.